Hi everyone, Assalamualaikum warahmatullahi wabarakatuh. I'm glad to see you again at MA3051. Today we will discuss Chapter 4, which is about traversability. There are two sections. First, Euler Tour. Second, Hamilton cycles. Enjoy listening. Euler became the father of graph theory as well as topology when in 1736 he settled a famous unsolved problem of his day called the Königsberg Bridge problem. There were two islands linked to each other and to the banks of the bigger river by 7 bridges, as shown in this figure, and the problem is stated in the following. Can we cross each of the 7 bridges of Königsberg once and only once during a walk through the town? And Euler settled this problem by showing that this walk cannot be done. By Euler, this problem was translated into graph theoretical problem with all vertices represent the areas and edges represent the bridges. So we have a graph with 4 vertices and 7 edges shown in this diagram. And this problem can be considered as the origin of graph theory. Before we see the famous theorem by Euler, let us define the following notion. A trail of G is a walk that travels each edge of G at most once. An Euler trail is a trail which travels each edge exactly once. Yeah? And a tour of G is a closed walk that travels each edge of G at least once. And we define as Euler tour a tour which travels each edge exactly once. So Euler tour must be a closed Euler trail. Finally, a graph is Eulerian if it contains an Euler tour. Now we have the famous Euler theorem here. A connected graph is Eulerian if and only if it has no vertices of odd degree. Okay, now we are going to see the proof from left to right. Let's say we have a graph G is Eulerian, so that means we have an Euler tour of G. Let's see be an Euler tour of G. So see this illustration, we can have, for example, C is starting from phi2 and then we are going to phi3, phi4, phi5 and then phi6 and phi1 and also we go again to phi2 and then phi6 and then phi3, phi5 and back to phi2. Yeah? So this is an Euler tour of graph G. Now assign an orientation for C, which is every edge is oriented. See in the diagram, so we have all an arrow to these edges. We start from phi2, so we go this way and then this way and so on and so on. So we assign every edge as orientation. And then every vertex V has the same number of edges going in and going out, right? So when you see in V2, you have one going out and then this one another one, so we have two going out edges and then two going in edges. So also in other vertices, because we have a closed trail, yeah. So the degree of every vertex V must be even. Now we are going to see from right to left. By contradiction, let G be a connected non-Eulerian graph with no vertices of odd degree. Yeah? And choose G with minimum number of edges. The smallest as possible, yeah, the number of edges of G. Now, since the minimum degree of G is at least 2, then G contains a closed trail C. Yeah? And choose C with the maximum length, yeah, as long as possible. Since G is not Eulerian, then G minus C has a component G prime with some edges. Yeah? And because the number of edges of G prime is less than the number of edges of G, the graph in the original, then G prime must be Eulerian, because we already assume that G is a connected non-Eulerian graph with no vertices of odd degree. Yeah? And G we taken as small as possible, yeah, in terms of the number of edges. So in G prime, we have the number of edges is less than the number of edges in G, then we conclude that G prime must be Eulerian. So we could join C and C prime. C is the closed trail, yeah, of G with the maximum length, and then C prime is an Euler Tour in G prime. So if you join C and C prime, then you will have a longer trail of G. So this is contradiction to the choice of C as the maximum length of a closed trail in G. As corollary, we have the following statement. A connected graph has an Euler trail if and only if it has at most two vertices of odd degree. Okay, now we are going to prove from left to right. Every vertex other than the start and the end of the Euler trail must have even degree, right? So the starting vertex and the end vertex of this trail can be having odd degree. So that means at most two vertices of odd degree in that graph. Now we are going to prove from right to left. If G has no vertices of odd degree, then G has an Euler Tour, right? This is by the previous theorem. So if G has two vertices, U and phi of odd degree, then G plus the edge UV must have an Euler Tour by theorem 4.1, right? Then C minus UV, if you remove again the edge UV, yeah, you will have an Euler trail, right? So the graph G itself has an Euler trail. So the corollary has been proven. Now, what about if G has one vertex of odd degree? Of course, not possible, right? By the handshaking lemma. Okay, so this is the end of our lecture. Thank you very much, and wassalamualaikum warahmatullahi wabarakatuh.